Hello, everyone. Today we are going to do a lecture on inverse Laplace transform and solving initial value problems. I think in our book, these are the section 7.5, 7.6, but I'm not sure. So we are going to start with definition of inverse Laplace transform. Definition. Sorry, a little bit of. Let me erase this, is too big. Okay, definition. If f of s is a given function and there is f of t, such that Laplace transform, sorry guys, I keep touching something that's not something I'm not supposed to touch. That Laplace transform of little f of t equals big f of s, then we are going to consider little f of t to be an inverse of big f of s. Well, basically, we are trying to kind of go backward from the space of transforms to space of normal functions. Let me write down is inverse Laplace transform of big f of s. We're going to start with example and then talk a little bit about properties of inverses. So our first example number 1. Let's consider big f of s equals 3 over s squared plus 25. And ask a question, which function produced this big f of s? So what is a little f of t, which we integrated with a core and got this big F? Well, what do we know? We know that Laplace transform of sine of at, where a is just a real number, is equal to a s squared plus a squared, right? And of course, s greater than 0. Now, unfortunately, the formula for sine is not matching exactly the formula we have for f of s, right? If a, for example, is 3, then we're supposed to have 9 here in the denominator, but we do have the 25. So we are going to modify a little bit big F, and we are going to represent f of s as, well, I think what we can do, guys, we can create 5 on the top and represent it like this, 3 over 5 over s squared plus 25. Now, well, you remember that we can cancel with 5 and that function is the same, right? But here we do have a square of 25. So what are we going to do? This is a constant, so we don't need to worry much about it. And this one is Laplace transform. This one is Laplace transform of sine of 5t. So what we can say that Laplace transform inverse of 3 over s squared plus 25 is going to be equal 3 over 5 and the sine of 5t. Sorry. Well, why we can kind of play with a constant? Well, remember that for integral, Laplace transform is actually integral, right? And the constant inside of the integral can be always taken outside. So this 3 over 5, sorry, somehow my 5 doesn't look like 5. This 3 over 5, when you when you put it under the integral and integrate, can be taken outside, or you can bring it inside. And this is why we can kind of just multiply our Laplace transform by it. Okay, So what else can we say about inverse Laplace transforms? Well, they're also linear, right? Linear means that, let me write it down. Inverse Laplace transforms are linear. Well, linear means that inverse Laplace transform of C1 F1 plus C2 F2 is going to be equal to C1 inverse of F1. Sorry, move it a little bit this direction. Plus C2 inverse of F2. Well, again, why does it happen? Because actual initial Laplace transform or Laplace transform of a function, like, let me write it down somewhere. This f of s, right? Remember how we define it. It's integral from 0 to infinity. And that's going to be f of t e to the power of negative st dt, right? If you do put a constant here, you can always take it outside, right? But when you go back, the function which was producing f, if you multiply it by a constant, it's going to produce f multiplied by a constant. So if you multiply somewhere here constant c1, then you are going to produce a Laplace transform multiplied by c1. So this is only consequences of the definition of original Laplace transform as integral, right? And you can, integrals are kind of linear. Okay, so I'm going to move to my next example, and let me move it up a little bit and kind of consider slightly more complicated function f and find out Laplace transform, inverse Laplace transform. So I'm going to use a different color. Example 2. Somebody is asking me to find inverse Laplace transform of 2 over s plus 5 minus s minus 2 over s squared plus 4, right? So first, I'm going to represent it like a linear combination of something for which I do know inverses. Well, because I do know direct transforms. So what I'm going to do, I'll start with taking this 2 outside of Laplace transform. I'm going to start with splitting this fraction into 2 fractions. So watch how I do this. So it's 2 Laplace inverse of 1 over s plus 5 minus Laplace inverse from s over s squared plus 4. I'm splitting this fraction into 2 fractions, number 1 and number 2. Okay, and well, because we do have a minus already and there is one more minus, we are going to have just Laplace transform inverse from 2 over s squared plus 4, right? Now we'll need to figure out which function produces this one, which function produces this one, and which function produces this one, and just combine them together. Well, what we know about this one, remember the table or the previous lecture, that this one is exponential function. So I'm going to copy 2 with just coefficient, right? And then I'm going to say that this is e to the power of negative 5t. Remember, for exponential function, it's s minus a, which is going to give you e to the power of at. So when you have plus here, it's going to give you a minus here. Right, next one is going to be the cosine, right? And I said cosine, I think it's going to be a sine, right? Well, what I see that, give me a second, guys. I'm trying to figure out. Okay, we're going to have minus sine of, oh, that's us, right? We have 2 over here, minus, well, plus, sorry, let me erase this. Minus cosine of 2t and plus sine of 2t. Sorry, confused with minuses. I was trying to figure out what is, well, because I'm kind of I made notes and I kind of messed with the minuses somewhere here. Okay, over here we have 2 and 4 is a square of it, right? So we are going to have a sine of 2t, like we had in the previous example, number and number squared, right? And in the first expression, we have s and s squared plus 4. 4 is the square of 2, so we are going to have cosine of 2. And the plus, because we had a minus here and the minus here combined into plus. Okay, sorry, I lost where I was somewhere. Okay, let's move to more complicated example. More complicated example is going to deal with more complicated fractions. So example number 3. We're going to consider a Laplace transform of 1 over s squared plus 4s plus 5. Well, if the fraction we have does not look like cosine or sine, right? Because they're supposed to have like square plus a square of a number. What are we going to do, guys? We are going to bring it to that form. I'm going to write down. So it looks like a over s squared plus a squared, right? Actually, it looks like Laplace transform of inverse of sine of at. The only thing is that we have trinomial instead of binomial in denominator, so we can always turn trinomial into binomial, completing the square, right? And that's what I'm going to do. So I'm going to complete the square for s squared plus 4s plus 5. And represent it as s squared plus 4s plus 4 and plus 1. This trinomial is going to complete the square s plus 2 squared in this one is just going to be separate descending one. Now I'm going to put it back into my fraction. So what I have Laplace transform inverse from 1 over s plus 2 squared plus 1. Now it looks exactly like sine of at, but we do have over here instead of s, like over here is s supposed to be just s, right? We have s plus 2. We do remember that this happens when we shift the function, right? The shift over here is going to be reflected as multiplication by exponential function. I'm going to write down the answer and then discuss it a little bit. So we have sine of 1t. Why is 1t? Well, because this is 1, right? This one is over here. And exponential function e to the power of negative 2t. Remember, when we multiply a function by exponential function, we are just going to shift the Laplace transform of it. And it's going to be shifted like as many units. So it's supposed to be s minus whatever is coefficient here, right? But because it's minus 2, we are going to have s plus 2. Okay, I'm going to write down how the property looks. So it kind of comes back from my previous lecture. So remember that Laplace transform of e to the power of at by f of t equals f of s minus a. So if you multiply your function by e to the power of at, you shift your Laplace transform of the function f by a unit to the right. Well, because we had plus over here, so it's like minus 2, so a equals minus 2. I'm going to put over here y and label that's y explanation, right? So a equals minus 2. Okay, well, next example. A little bit more on examples and then how we solve actual initial problems using this example. So one more example. Example number 4. F of, oh, sorry guys, I'm sorry. Suddenly I again pressed something and kind of stretched it too much, I guess. So f of s equals 3 over s minus 1 cube. And I'll need to figure out inverse Laplace. So inverse Laplace of f is a question? Well, to us, if we forget for a second about like -1, which is just a shift, it's going to look like Laplace transform of t squared, right? Laplace transform of t squared is equal like 2 factorial over s cube. Well, you probably remember from our lecture, right? Now, what is going to happen when we apply -1 here? Well, that's going to be a shifted Laplace transform. So I'm going to kind of modify a little bit my function to make it fitting into this one, right? Because Laplace transform of t squared equals 2 factorial over s squared, which is like 2. I'm going to write down, which is 2 over s cube. But here we do have 3 over s cube. So we need kind of adjust this 3 to make it like 2. So I'm going to write down Laplace transform inverse. And here I'm going to write down 3 over 2. And here I'm going to write down 2s minus 1 cube. Right? Good. So I'm going to put 3 over 2 outside. Now this one is going to produce actually t squared, right? And I have to multiply by exponential function e to the power of, well, it's supposed to be s minus a according to this formula, right? S minus a. So my a equals 1. So it's supposed to be 1t. Well, you don't have to write down 1t. You just can write down e to the power of t. So 3 over 2 t squared e to the power of t. So again, I'm referring to the same formula here, the shifted Laplace transforms. Okay, very good. Let me write down that this is a shift. Well, now I'm going to give you an example of solving initial value problem using Laplace transform. Well, it's not only Laplace transform which we are using, right? We are using also formulas for derivatives, but Laplace transforms is going to be a useful part of our solution. So my last example is going to be example of solving initial value problem using Laplace transform. And the problem is going to look like this: y fourth derivative minus 16y equals 0. Because it's initial value problem, we have y of 0 given and equals to 1, y prime of 0 equals to 0, and y second derivative of, sorry, too many bars, sorry, y second derivative of 0 equals to -1, and y third derivative of at 0 equals 0. Well, again, remember that the formula which is used to modify this equation into Laplace transform of this equation is using initial conditions. So Laplace transform likes to solve initial value problems. Normal methods are solving first general problem and then use initial values. Laplace transform starts with initial values in the beginning. So, well, we have some kind of random coefficients here. Also, you probably wonder why equation looks so weird, like a fourth derivative minus 16y. Well, it looks so weird because generally speaking, it's not going to be very easy to find inverses of Laplace transforms. It's not going to be like a very short problem. So I'm trying to pick up a problem where you can find it a little bit easier, right? First, we are going to start with use of Laplace transform on equation. So I'm going to apply Laplace transform to fourth derivative and write down that it's going to be s to the power of 4. You probably remember the formula, like Laplace transform of y minus s cube y of 0 minus s squared y prime of 0 minus s y of second derivative of 0 and minus y a third derivative of 0, right? So that's just a fourth derivative, right? How it goes into Laplace transform. And I'm going to use my initial values, plug them in over here. So my first y of 0 equals to 1. This one equals to 1. That's first derivative equals to 0. And this one equals to -2. And the last one equals to 0. So I'm going to have s to the power of 4 Laplace transform of y. You know, in some books, you are going to see a big Y instead of writing down Laplace transform of Y. I think I'm going to keep writing down Laplace transform of Y, but again, that's up to you how you write it up. Then the first one is going to give me -s cubed, right, multiplied by 1. The second one is going to disappear, and the third one is going to give me plus 2s. Let me double check it. Yes. Okay, now I'm just going to, well, Laplace transform of this term is going to be just -16 Laplace transform of y. So I'm going to plug in this fourth derivative and use Laplace transform of this term to combine everything into one equation. So I have Laplace transform of, why did I write down s to the power of 2 here? There is no explanation actually. Was power of 4 and suddenly became power of 2. That was power of 4. I absolutely had no reason to change it to 2. So s to the power of 4 Laplace transform of y. I'm just copying this part, -s cubed plus 2s and minus for this term 16 Laplace transforms of y and equals to 0. That's my equation in Laplace transform space. Now what I'm going to do, I'm going to keep all Laplaces on the left side and all variables as on the right side and kind of take this Laplace of y outside of parentheses. So I have s to the power of 4 from this term, and this term is going to produce 16, right? And moving these two terms to the right side is going to give me s cubed minus 2s. And the last step left is Laplace transform of y. We will need to clear it from s. We're going to divide by s to the power of 4 minus 16. So it's s cubed minus 2s divided by s to the power of 4 minus 16. So now basically we already solved the equation because the only step left is to find y, which we can find by using inverse Laplace transform. So Laplace transform of unknown function y equals to this means that unknown function equals inverse of this Laplace transform. And I'm going to just write it down. And mostly, guys, solving initial value problems using Laplace transform is a search for inverses because everything what happens before is just algebra, right? Well, just, you know, using a formula for derivative and then combining everything, just like plain algebra. So we'll need to deal with this function, with this fraction, and what we'll need to do is to decompose this fraction into kind of simple fractions, and that's going to take about like next 20 minutes. That's where we do the work for differential equations. So we are going to decompose it. S cubed minus 2s over s to the power of 4 minus 16. Well, I'm going to start decomposition with decomposing denominator into simple factors. So I have s squared minus 4, s squared plus 4. I cannot decompose this one, but I still can decompose the negative, the subtraction of 4, right? S cubed minus 2s. It's s minus 2, s plus 2, and here s squared plus 4, right? So generally speaking, this one is irreducible. We cannot decompose it any further. And we are going to have two simple factors and one irreducible, which are going to produce for me three fractions: a over s minus 2 plus b over s plus 2. And because this one is a second order, we are going to have cs plus d over s squared plus 4. Now we just need to find A, B, C, and D. Well, there are different methods to do this, right? You can multiply everything, right? And then compare the coefficients. That's a standard way we usually teach in Calculus 5b. We kind of bring it to common denominator, multiply everything here, and compare the coefficients of s cube, s square, first power, and 0 power of s, and get like, well, I think four equations for 4 coefficients. It's just linear algebra. But I want to show you a different way to do it, slightly different way to do it. But if you don't like it, you can use a standard way. I really don't know which one is going to be faster. So what I'm going to do, guys, I'm going to find the roots for all the factors. So roots. Well, the first factor is going to have s equals 2, right? Turns it into 0, s equals -2. And this one does not look like a good equation, but actually you know that if you set it up to 0, you are going to get s equals plus minus 2i, right? A complex root. You probably tell me like, okay, what should we do now? Well, now we'll need to kind of multiply everything to bring it to common denominator, right? So what is missing here? Let me use a different color. What is missing here? Here is missing, I wanted to actually use orange. Here is missing s plus 2 and s squared plus 4. What is missing here? S minus 2 and s squared plus 4. And over here, we are just missing s squared minus 4. I combine these two terms together into one. But again, you can write it down as you like, but that's just like a way I did. Okay, I'm returning back to my green and writing down like my expression. So on the left side, I have s cubed minus 2s, this one, right? On the right side, after I bring everything to common denominator, I can drop both denominators because they are same denominator here for s cubed minus 2s and the same denominator for this expression. And write it down as a. I'm not going to open parentheses. I'm just going to copy everything. So it's going to be a s plus 2 s squared minus 4, sorry, plus 4, plus b s minus 2 s squared plus 4, and plus cs plus d s squared minus 4. Again, s squared minus 4, it's a product of s minus 2 and s plus 2, right? Now, what I'm going to do, guys, I'm going to start substituting my roots into this expression and kind of harvest zeros when root is going to be something like turning the factor into 0. So I'm going to start with my first root s equals 2. If I plug it into left side of my equation, I'm going to get what? 8 minus 4. And on my right side of an equation, I'm going to have a. And if I plug into here, it's 4, right? If I plug into here, it's 4 plus 4 is 8, right? Plug in 2 here is going to give me 0 because 2 minus 2 is 0. And plug in 2 here is going to give me 4 minus 4 is also 0. So I don't have anything else here, and I can calculate a easily. And my a is going to be what? 8 minus 4 is 4 divided over this 4 is going to give me 1 over 8. Well, you can do the math on your own. I think you're going to get the same answer. So my next root is s equals -2. I'm going to substitute the same way. Here is going to be -8. Here I'm going to get -4. Not -4, +4 actually, just because minus 2 and minus are going to cancel. Now, what I'm going to have on this side? Well, -2 is going to cancel s plus 2 into 0. So we are going to lose this term, right? -2 is going to give me b multiplied by -4, and -2 is going to give me 4 plus 4, which is 8. This term is going to disappear too, because -2 square is -2 square is going to give me 4 minus 4 is 0. So this is going to disappear, and I can calculate b term also easy. So here I have -4, and I divide by this -4, and I'm going to get 1 over 8 again. It doesn't look very nice. 1 over 8 again. So now, what should I do with these complex roots? Well, let's see how I work with them. If you don't like it, you can do it a standard way. You just can multiply everything and compare the coefficients. But I don't want to do linear algebra equation here. So I'm going to deal with s equals 2i. my next root. I'm just going to plug it as usual everywhere. So s equals 2i is going to give me what? 8i cube for the first term and minus 4i for the second term. It's just like because 2 by 2 is going to give me 4 and there is I. Now, what is going to happen here? Well, guys, because 2i is one of the roots of s plus 4, this term is going to disappear, and this term with b is going to disappear. The only term which is going to stay is this term with c. So let's see what we are going to have. I'm going to put zeros for first two terms so you can kind of understand what happened. Now, for the remaining term, I'm going to have c by 2i plus d, right? I'm plugging in s. And for this one, I'm going to have 2i squared minus 4. Now I'm going to simplify this expression a little bit, and left side and right side, I'm just going to get a simple equation for c and d. So here, guys, when you cube I, you are going to have I square, which is going to give you minus 1 and 1 more I. So it's actually minus I and 8 and minus 4i, which we're going to give us minus 12i on this side, right? What are we going to have on the right side? Well, this one is 4, right? I square is minus 1. So we have minus 4, which is going to give us minus 8. And I'm going to have minus, if I multiply this minus 8 by 2, minus 16i by c, and minus 8d. And that's kind of simplified form. Now, what I'm going to say, guys, two complex numbers are equal. This is complex number here, right? This is complex number here, and this is complex number here. Two complex numbers equal if real part of the first number equals to real part of the second number, and imaginary part equals to imaginary part, right? So now I'm going to compare. Okay, I do have only imaginary part here, so I kind of can say that minus 12 is supposed to be equal minus 16c, from where c equals minus 12 over minus 16, which is going to give me what, 3 over 4, right? 3 over 4. What is going to be my d? Well, there is no real part here, so my d is going to be equal to 0. D equals to 0 because there is no real part. 0 real part is going to be equal to, well, that's it. I found my coefficients. So now I'm going to write down decomposition and the final answer. Let me move it up. I'm going to return back to green color because kind of this one is just explanation, right? So my decomposition s cubed minus 2s over s to the power of 4 minus 16 is going to be 1 over 8 s minus 2 plus 1 over 8 s plus 2 and plus 3 over 4s divided over s squared plus 4. We're going to miss the fourth fraction because d was equal to 0, right? D was equal to 0 means that there's going to be no fraction d divided over, or no fraction, no part of the fraction. We had a fraction cs plus d, so there is going to be no d, no term like plus d. It's going to be plus 0 here. Okay, now we are going to apply Laplace transform to this and get our function y, right? Y equals Laplace inverse of 1 over 8s minus 2 plus 1 over 8s plus 2 and plus 3 over 4, 1 over s squared plus 4. What do we know? First, we can take 1 over 8 outside, right? The Laplace transform of this is exponential function, right? So it's e to the power of 2t, right? Well, according to formulas in a table or from the lecture, this one is going to be another 1 over 8 e to the power of negative 2t. Why negative? Because it's plus 2. The formula has s minus a, and then it's at. So if it's plus, we are going to have like minus. And the last one is going to produce, I think, a sine. No, let me see. I'm missing s over here. I'm thinking like, why do I was always thinking about cosine over here, but okay, guys, I'm missing s over here. When I was copying, I forgot to copy s. Right. So this one is going to produce cosine of 2t right inverse. So I'm going to have 3/4 cosine of 2t. Well, again, because this is Laplace transform of cosine of 2t, right? Somehow I'm missing s, but otherwise that's the final answer. What is good here? Well, we do not kind of differentiate anything, right? We do not have integrate anything. We just use algebra to find a big F for a solution. And then we use decomposition, which is also algebra, and table, which is well known, to figure out the kind of inverses. And it solves a problem right away. You don't need to kind of find coefficients C1 and C2 and C3 and C4. You have it all right away ready. My suggestion, guys, Laplace transform is not very like let's say transparent. When you start working on it, your intuition probably is not going to give you like if you're doing mistakes somewhere or not. My suggestion, whenever you solve equation by Laplace transform, you always can try to solve the very same equation using standard methods of undetermined coefficients, right? Or like, you know, you first write down characteristic equation and then use undetermined coefficients if like you have any non-homogeneous equation. Okay, what is going to happen for non-homogeneous equation? By the way, our equation was homogeneous, right? Equals to 0 over here, right? What is going to happen to non-homogeneous equation? Well, if you have non-homogeneous equations, there is going to be a function here. For example, sine of t. Well, use the Laplace transform to sine of t, convert it into the fraction, and then this fraction is going to participate in decomposition and make your life even harder. Well, I would say that's the hardest part of Laplace transform is here. How do we kind of avoid doing any integrals? Well, guys, we don't avoid doing integrals. We just did the integrals when we obtained the table. Remember, to obtain values from the table, like Laplace transform of certain function, we were integrating. So it's kind of, we prepare integrals before we solve differential equation and then use them ready integrals. But we do integrate somewhere. We just integrated before we started solving equation, not like after when we solve actually it. Okay. Well, I think that's it for this lecture, and thank you very much for your kind of, you know, participation and attention. So I'm going to finish at this point, and I'm going to post the whiteboard notes on my Canvas too, but you have better notes which are like paper ones. Okay.